Hello, I'm Rajib, and here I am to present our IoT project. So, the goal of our project was each IoT device will work as an independent server. Any server will be able to generate operations randomly, and all the other servers will have eventually consistent states. So, that was our goal, and how to achieve this goal. So, here is our approach. A node will randomly generate one of three operations like let off, let on, or let toggle. All the nodes will propagate any new operation to their neighboring nodes. Each node will maintain a logical clock and history of operations. And when a node will receive an operation, so it will work with two different cases. Like if it's a new operation based on logical clock, then it commit immediately. And if it's an old operation, then a node will roll back all the previous operations from their own history and then commit again after applying received operations. So as there will be some missing messages, all nodes communicate with their neighboring nodes in timely manner to sync their history. So now I'm going to talk about some challenges and corner cases of this solution. So the firstly, data transfer is unreliable. No certainty of reaching the message even to the nearest node. If we have a state like this, for example, the IoT devices are in state like only the red LED is turned on. Now, suppose one IoT device generated a new operation to turn on the blue light and send and broadcast this message to other IoT devices. So there might be a possibility that this IoT device got the message. This one also got the message, but this one didn't get the message. So this is an inconsistent state. Another corner case is like sometimes data is corrupted. For example, suppose this node generated a new operation with this node ID and its operation like toggle and with color red. So there might be a possibility that these two node get the actual messages as expected, but this node got a corrupted data. That doesn't mean anything. So we have to solve this issue. Another corner case is like data transfer can be unordered. For example, these two nodes simultaneously generated two operations. Like it generated like randomly generated off the rate, so it's just executing the red light off, and it's toggle the rate. So it will basically it's already turned on. It will definitely turn off now. But what if this message goes unordered in different nodes? So this node receive the message first off then toggle, and this node receive the message first toggle then off. And then after applying these operations, so we can see this is an inconsistent state for both of these. So another problem is the data transfer MTU. I mean, when we send a packet during sky mode, it is limited to roughly it's 125 bytes. So we can't send more than this data in single packet. So we need to use a limited memory to send maximum number of latest histories. We can't send all the histories. We had to send the latest some number of histories to sync the data. So how we achieve this proposed solution? For the first case, that is unreliable. So some data can be missed, but later we can sync the data by sharing the history to the neighbors. When the data is corrupted, we analyze the received data. We try to detect if the data is corrupted, and we just keep that data if it's corrupted, because in later we'll get actual data if it's available in my neighboring nodes. So data is unordered. It's a pretty simple solution. We use distributed logical clock to order data. And memory limitation, so we have to use memory so efficiently so that we can send maximum number of data in a single packet. I mean maximum number of operations. So how we manage memory to maintain the history? So we try to achieve to maintain the history with the lowest memory as possible. So we used only 3 bytes to store a single operation. uh, for first 6 bits is used for node id, then 2 bits used for operation, and 2 bits used for color, and next 14 bits used for logical clock. So 14 bits can be, we can maximum value of 16384 value, so it's more than enough. So as a particular values are overlapping in multiple bytes, we needed to write some encode decode mechanism to achieve values based on received data. Yeah, we have a limited packet size, roughly 125, so we sent 25 latest operations in timely manner to sync the neighboring nodes. We have limited memory in device, so we had to reset every device when any of the device processed 1000 operations. So this is our limitation for managing the history. Yeah, so now I'm going to show you the live demo of our project, how it looks like now. So for this, uh, um, yeah, so now let me pause. So first I will show you the situation for 9 nodes. So yeah, so it's already 9. So try to start it from the beginning. So yeah, it's taking some time to data. So we start our project. Let's say we don't have any speed limit, so it will run as fast as possible. So here we can see all the so all the nodes are working independently. They can generate new operation and propagate to others, and based on this operation, all the nodes need to be in consistent state. So if we just roughly pause in a certain situation, we'll see uh, what's happening there. mm, let's sorry, let's pause. Yeah, so we have a situation here. So here we can see after sending 34 new operations, so all the nodes are in a consistent state. So after 34 iteration, everything is in consistencies. So let's go further. Yeah, let's pause here. After 36, I mean it added the new 2 operations, consistent state. There are some cases there will not be in consistent state. Maybe you can generate these. Yeah, so here we can see these 2 nodes is not in consistent state, but these other nodes are in. So here we have 2 different state, but if we run further, we can see everything will be synced. Yeah, see, now everything is synced again because the history is transferred during this time. So let me run this project for 25 nodes. Let's see what happens then. So for this I need to write this as 25, and let me reload this so that it can run from the latest code. Yeah, so let's say there is no speed limit for this. So now the solution is started for 25 master nodes. So after some time they will start propagating messages, new operations to other nodes. So let us just wait for a bit. Yeah, so the first operation is transferred to all the nodes. So here we can see the history size in probably it's on node 5. So in node 5 it's the history size is 4. So if we pause here, no, not in on the middle of transfer. Let me, yeah, so just pause here. So here after 8 operations, every nodes are in consistent state. So if we go further, let's see what happens next. Yeah, so let's just pause here. So here we can see after 17 new operations, yeah, everything is in consistency. So it's working really great after our implementation. It's really working great. But during in certain lab, we had a problem like just sending toggle operation. It didn't work that much. Now it's really in pretty good state, as I can say. So how good our solution is, for this we have written a nice analysis um, in Python, just analyzing the logs of 9 nodes, 15, 25 nodes and 49 nodes. So I can show you the evaluation part. So let's see how how good our solution is. So let me run the Python program. Yeah, so this is the consistency test for 9 nodes. So after uh, processing like 1200 seconds. So this is basically this row basically means the seconds, and this row, sorry, this axis uh, means number of operations received. So we we just got the idea like if node get all the operations, then it is in consistent state, because uh, if it gets all the operations, it can order using the node id and the logical time. Then we can say that this is in consistent state because it got all the operations. Now to plot this graph, we have just selected randomly 5 different nodes of among 9 nodes. So here we can see, so node id 2, 5, 6 and 8 and 9. For these 5 nodes, we generated the graph and which time it got the which number of messages. So here you can see the blue line, that means the node id 2 has less number of messages in 1000th second, and node id 9 has more messages than this. But if you go further, after some time, it merged with 9. So as you can see, even though it didn't have all the messages, after some time it got all the messages. So we can see that this data become eventually consistent. So here is the evaluation for 9 nodes. Let me show you evaluation for 25 nodes. So 25 nodes is work much more better than 9 nodes. So here you can see it just selected randomly 5 different nodes, and here all the data almost merge with other one. So everything is everything is consistent. uh, Sometimes it see the red line node id 1, sometimes it didn't get all the messages, but eventually after some time it merged with all the operations. So it is also working good. And for 49 nodes, it's all more better than 25 nodes. See, in all state, all the 5 different random nodes, they are in consistent state all the time. So that's how our evolution look like. And if we run the analysis again, it will always select the random 5 nodes. Then you can see now 81972. Sometimes it's not in the consistent state, and eventually it become in consistent state. And for 25 nodes, here node 25 has some problem, but after some time it is in consistent state. So that's how our solution work. Yeah. So uh, as I'm not talking about the code much, because this code is already explained on the slide first I explained. So yeah, that's all our project presentation is. uh, Thank you for listening.